Let's look at AP Live. This is continuing with our review worksheet for AP exam, number 15. Let f of x be equal to this polynomial function here, x to the 4 plus ax squared plus b. The graph has a relative maximum at 0, 1. So relative maximum occurs when our slope is 0. And an inflection point when x equals 1. So an inflection point occurs when f double prime is equal to 0. The values of a and b are. So I'm going to first start off with f prime. Set f prime equal to 0 and see where that takes me. So f prime, power rule, x to the 4th becomes 4x cubed, ax squared becomes 2ax, b goes away to 0. We can set f prime equal to 0. And that leads me to this point. Doesn't seem to allow me to go further beyond that, because if I plug 0 in for x, I'm going to get 0 over 0 equals 0. That doesn't really help me out, so we'll put that on hold. Let's go ahead and find the second derivative, so f double prime. That gives us 4x cubed becomes 12x squared, 2ax becomes 2a. We're going to set f double prime equal to 0 because we know that is true about that there's an inflection point when x equals 1. Replace x with 1. Now we're able to kind of solve for a little bit. This equation is more helpful in terms of solving for a. So let's replace x with 1. We get 12 times 1 squared plus 2a equals 0. Subtract negative 2 to the other side. Negative 2a. Divide both sides by negative 2. We get a equal negative 6. So now let's use this and update our original equation. So a gets replaced with negative 6. Okay. Replace x with 0 and y with 1. And then we can solve for b. So this wipes out everything except for b is equal to 1. A equals negative 6, b equals to 1. So we have our two values. All right, number 16. F prime graph is shown. The derivative graph is shown. Answer the following, which find the x value where the absolute minimum occurs. I'm going to create my two sign lines that I can build off of my f prime graph. Anything above the x-axis represents positive slope. Anything below represents negative slope. Anything on the x-axis is where slope is 0. So I have my endpoints 0 and m. My critical point at k. Between 0 and k, I know my graph is above the x-axis. That's going to indicate my original graph is going to be rising from all the way from 0 to k. And then from k to m, all this is below the x-axis, so I know that on my original graph, my slope is going to be negative from k to m. So I know that the graph is going to rise to k, and it's going to fall after that. So we know k is going to have to be the absolute maximum. And then the absolute minimum is going to occur. We know that from 0 to k is going to be rising. Let's call this 3. Okay, I'm just going to give a random number here, 3. So let's say from here it rises 3 units to a y value at k, and then it's going to fall. Let's say this is negative 6. So it's going to fall negative 6 all the way to the graph at m. So the graph is going to rise a little bit, but it's going to fall a lot more, and so we know that the absolute minimum is going to have to be at m. Right? If the graph starts at a point, it rises a little bit, and then it falls continually until it reaches the endpoint, we know that endpoint is going to have to be where the absolute minimum is. So absolute minimum occurs at x equals m. Since our graph falls more in the interval from k to m than it does rising from 0 to k. Find the k value where there's an absolute maximum. We talked about this, how the graph is rising until a certain point at k, then it falls. Because it rises, then falls, it's not going to rise back up again, so we know k is going to be the absolute maximum. Part C, sketch a possible graph of f of x given that f of 0 equals negative 2. So I'm going to sketch a possible graph, but first let me gather some information about the second derivative sign line. I know that my graph wherever there's peaks and valleys, these are going to be points of inflection off the original graph. And then wherever the graph is rising or falling, that's going to correlate to concavity. So we know there's a point of inflection at J, there's a point of inflection at L. From 0 to J, the graph is going to be concave up because this graph is rising. Here, concave down from J to L, and then concave up from L to M. So here's a possible graph here. Just based off the sign line from 0, I know I have 0, -2 being my order pair here. My graph is going to rise until I get to a certain maximum K, and then it's going to fall after that. So I just use the dotted line to kind of help me map my very general path. So now I'm going to get more specific here. I know there's a point of inflection at J and L, so I'm just going to highlight those points along the path of my graph. And now I'm going to give it the curvature that it needs within each of these intervals. So from 0 to J, I'm going to make my graph concave up shaped. From J to L, I'm going to make my graph concave down shaped. And then from L to M, I'm still going to be decreasing, but now I'm going to give it that curvature. Part D, sketch a possible F double prime graph. So F double prime graph, we know that our y-axis represents concavity, so anything above is concave up, anything below is concave down, anything on the x-axis are points of inflection. So I know my graph is going to be concave up, and it's going to have to reach these x-intercepts at J and L. So concave up, it's going to have to connect to that point above the x-axis. From J to L, concave down, so below the x-axis. From L to M, concave up above the x-axis. Table gives selected values for differentiable function g, so the graph is continuous and differentiable throughout the entire function g. What's the least number of times that the graph is going to reach a y value of 3 in the given interval? So we know the graph is going to have to connect through these points, so it's going to have to reach 3 from -4 to 5, right? It's going to have to eventually move up to that y value of 3, or at least reach past it. And then from 5 to 2, it's going to drop to 5 to 2, which is going to cross 3 another time. From 2 to 5, it's going to rise, and it's going to reach 3 another time. But then from 5 to 10 to 20, the graph doesn't have to dip below, so we see that there is intersection here, intersection at 3 here, intersection at 3 there. So we know there's 3 times. By intermediate value theorem, the graph has to connect between a lower and higher y value, so it will reach a y value of 3 at least 3 times on that interval. Okay, part B. What can we conclude about the mean value theorem from 0 to 12? So we know that mean value theorem says that whatever the slope is between the endpoints, as long as our function is continuous and differentiable, that average slope is going to have to be shared by an exact slope somewhere between 0 and 12. So let's figure out what is the slope between our endpoints that we can guarantee. So here's our slope formula, change in y over change in x. So that's going to be y value is 20. 20 minus -4 divided by change in x, 12 minus 0. So we get 24 over 12, which is 2. So we know that because the slope between the endpoints has steepness of 2, we know there must be at least another point on the graph where there's a slope of 2. So just to demonstrate that, let's say we had the first order pair at 0, -4. We have a second order pair at 12, 20. Because there's a slope of 2 between those endpoints, we know that somewhere between there must be at least another point where it's going to share that exact same steepness. Okay. So since slope of the secant line, right, is a slope of 2, there must be at least one point on the interval from 0 to 12 where the slope of the tangent line is also 2. Okay. For part C, can Rolle's theorem be applicable on the interval from 2 to 8? So with Rolle's theorem, it's similar to mean value theorem, but it's not just guaranteeing any slope. It has to be a slope of 0. So the only way we can guarantee a slope of 0 is we look at the endpoints and see if they share the same y value. So we're looking at between 2 and 8. They both share the same y value of 5, which means that if we connect 2 points from one to the other, it's going to be a horizontal line. And because of that horizontal line there, we know there's going to be another slope of 0 somewhere between 2 and 8. Okay. Since endpoints have the same y value, there must be a slope of the tangent line that's also equal to 0. Okay, number 18. Function g is differentiable and increasing for all real numbers. There's exactly 2 points of inflection of the following, which could be the graph of g prime, which is the derivative of g. So if we're looking at the derivative graph, we know that our axis represents slope. Anything above is positive slope. Anything below is negative slope. Now we know the graph is always increasing, so we know the f prime graph has to be all sitting above the x-axis. Since g of x is increasing, our g prime will have their entire graph above the x-axis. So we know we can eliminate A, B, and D since we have portions that is obviously below the x-axis. So we're down to just E and C here. Now we were looking for 2 points of inflection. So points of inflection are represented on a G prime graph as peaks and valleys or max and mins. So we want 2 peaks and valleys in the graph that is purely above the x-axis. So we see that there is a relative max there, there's relative min there. These are both points of inflection. Here there's only one relative min, so we have 2 points of inflection, there's only 1 point of inflection. Answer choice C.